My name is Michael Gall, presenting this paper with Teresa Bulger, who could not be here tonight. But the paper is titled "Not Your Father's Country Bridge, the 1792 Stone Arch Bridge over Stony Brook in Princeton Township, Mercer County, New Jersey." The State Route 206 Stone Arch Bridge over Stony Brook in Princeton Township, Mercer County, New Jersey, is the oldest continuously functioning bridge in the state. This triple arch bridge was originally built in 1792 and by 2016 required rehabilitation. Despite modifications, much of the original bridge's fabric was preserved intact as a result of a bridge widening effort in 1916. Here, Teresa and I discuss the documentation of a nearly complete 18th century bridge, termed here as a legacy structure, ensconced within later bridge additions. Legacy structures, or infrastructure features preserved by later additions or replacement structures, have the potential to retain engineering and design information from the past. In this case, intact structural elements below the present bridge deck revealed a distinct engineering style used in 18th century England that was transferred to New Jersey by federal period bridge builders and possibly elsewhere. Richard Grubb and Associates' involvement in the project began in 2016 after a partial parapet collapse. So for those who don't know about the structural terminology for bridges, the parapet is the portion of the bridge that sticks up above the roadway along the side of the bridge. The bridge is located within several National Register listed historic properties, which you can see here. They're outlined in different colored polygons. Dynamic cultural resources constraints were in place, and early conversations were needed with the historic preservation community to ensure preservation concerns were addressed. Some of these aspects included HAIR documentation, that is historic American engineering record documentation, and archaeological monitoring during construction. The replacement of an adjacent 1896 floodplain bridge, which you can see here at the top, and the stabilization of the adjacent 1714 Worth's Mill ruins were also necessary. And you can see the stabilized portion of that mill ruins building in the lower right. Archaeological monitoring of infrastructure projects, particularly bridge, road, and dam projects, often reveals evidence of much earlier legacy structures that offer opportunities to document design techniques from the past. Identification of several prior legacy structure examples in New Jersey highlight the hidden complexity of such archaeological features and the insights they provide regarding historic technologies. Among these is the LEDDELL Pond Dam Removal Project in Mendham Township, Morris County, New Jersey, adjacent to 18th century mill ruins. Removal of a 20th century concrete dam exposed well-preserved remains of a wooden cribbing legacy dam on the upstream side of the modern dam. The wooden dam was built of stacked hewn logs secured in place with lap joints. And lap joints are very similar to like Lincoln log construction. To form a wedge-shaped profile, a section of the largest log was removed and submitted for tree ring dating or dendrochronology, suggesting its construction around 1750. And here you can see elements of that bridge. So we have in the upper left-hand corner, orange, blue, and green different colored logs, and they just represent the different layers of stacked hewn logs within this bridge. In the bottom left, you can see the concrete bridge concrete dam that was present. And in the center bottom image, you can see portions of these hewn logs that were exposed during construction. Dam breaching in FINESVILLE, Powhatan Township, Warren County, required removal of an existing 1950s dam, behind which a legacy wooden cribbing dam, a wooden sluice, retaining walls, and a much earlier 1750s dam were exposed. Tree ring dating of the cribbing dam indicates it was constructed in 1803. And here you can see part of that dam was originally exposed in this black and white image on the lower left before the concrete dam was constructed in the 20th century. The space between the logs was rock rubble filled, and the top of the dam was sheathed in milled wooden planks, which you can see here on the bottom right. Replacement of the Moseley Road Bridge over the north branch of the Raritan River in Mendham Township, Morris County, New Jersey, located next to a former 18th century iron bloomery forge, exposed a series of horizontally laid, buried, parallel logs at the river level behind an existing 20th century concrete bridge abutment. The logs were documented and represent an early wooden ford crossing within the river. Tree ring dating placed the log's felling date to either 1729 or 1745. So it was a very early wooden ford crossing within Mendham Township. A large pair of 18th century 4-foot long iron bloomery forge tongs were also found behind the existing bridge abutment. And you can see those large iron tongs here and how they would have been used in the iron manufacturing process here in the lower left. In 2015, Richard Grubb and Associates excavated test pits for the Jersey Avenue pedestrian bridge in Jersey City, Hudson County. Excavations in the creek floodplain exposed the remains of a deeply buried wooden plank road built between 1877 and 1883 using the Nicholson paving method. The boards were horizontally laid with their long edge oriented with the road axis and were underpinned by thicker timbers laid perpendicular to the wood plank road surface. And here you can see where we had breached that initial level of the road and where you can see the perpendicular boards that secured that road bed in place. Based on these and other examples, it was highly likely that original elements of the 1792 Stone Arch Bridge remained intact between the 1916 bridge widening sections. And I just want to point out, I thought this was pretty cool. A little bit of a college tag on the bridge crest here. You can see it says Rush 02. So in 1902, the Princeton University students were doing some graffiti on the bridge, which I thought was a little neat. Historic documents indicate that the Stone Arch Bridge was commissioned in 1791 and constructed in 1792, likely by local stonemason William Worth, and replaced an earlier bridge as one of several projects after the American Revolution that were part of an infrastructure rebuilding effort. The triple arch design of the Stone Arch Bridge includes 3 barrel arches with an additional tail race arch at its southwest end. And that arch you can see slightly in this image, and that was associated with the mill race that extended from the river through Worth's Mill to turn the water wheel and exited out of the bridge here. Bridge repairs took place in 1826 and later in 1891. 5 years later, in 1896, the bridge's roadbed was raised with the installation of macadam pavement, and fill was introduced at the bridge's ends to achieve a gentler slope at its crest. In 1916, the bridge was widened by 10 feet, and you can see that widening effort here. So this is the original bridge footprint, and these 2 red kind of pie-shaped wedges represent the area of the bridge that was widened in 1916. In 1935, HABS, that is Historic American Building Survey, reveals that within the bridge's arch rings, 2 construction episodes are evident. And this is just one of the sheets from the HABS drawing, this sheet on the lower right. Historic English masonry arch bridges represent a close analogy for 18th century New Jersey masonry bridge design, as many settlers of the state trace their roots to and main ties with England. Documented 18th century English stone country bridges in rural locations like that of Princeton's Stone Arch Bridge have a distinctive construction style. The stone arches of these bridges were typically built of local schistose. The more regular stones were chosen to form the arch faces, while the more irregular stones were tightly fitted to make up the barrel arch, with mortar poured in afterwards. The mortar was poured in at the top and then hidden from view. The close fit of the stones with minimal mortar allowed the arch thrust to be transmitted through the stones rather than through the mortar. As a result, the large forces at the contacts between stones ensured large enough friction forces to support each stone until its decay affected the stone itself, rather than the mortar lifespan. Notably, among documented country bridges in England, the spandrels of all these bridges were filled with gravel or earth. Bridge deck and infill removal of the Stone Arch Bridge exposed 18th century bridge elements and later bridge modifications. Archaeological traces of several building episodes were evident. In 1916, the bridges widened and straightened, a modification that is apparent in the form of two wedge-shaped concrete extensions, one each on the north and south sides of the bridge. The widening effort resulted in a straightening of the initial S-shaped approach for the bridge. During the widening effort, the original parapets for the bridge were cut to the new bridge deck surface in the center of the bridge, and the parapets near the bridge's approaches were left intact, or at least partially intact. The new poured concrete widening sections were faced with red shale on the spandrel's exterior, and new parapets were constructed. Between the 1916 additions, survived an almost fully intact 1792 Stone Arch Bridge. I just want to point out, so these are granite, very large granite stones. This one has a pointed edge, while many of the other ones were simply square blocks. These were recovered from the base of the creek during the rehabilitation effort. And what we think these represent are cutwater, which would have been at the base of each of the bridge piers to basically cut ice that approached the bridge as the river flowed through the arch openings. And this was a way to prevent the ice from damaging those piers. When the bridge was widened in 1916, these were removed because those piers were expanded in size. And what appears to have happened is the builders at that time were using concrete instead of the stone, and just discarded the stone back into the river.
The barrels.
The new poured concrete widening sections were faced with red shale spandrels on the exterior side, and new parapets were constructed, as I said before. Between the 1916 additions, survived an almost fully intact Stone Arch Bridge, which you can see in this plan view drawing once we had exposed the footprint of the bridge. So this area is the original bridge. It was kind of an S-shaped curve, and these are the poured concrete new spandrels and bridge portions that were added in 1916. When constructed, the Stone Arch Bridge was designed with 3 main arches over the Stony Brook. A 4th, smaller arch at the bridge's west end carried water for the Worst Mill tail race under the structure. The main arches were built as round barrel arches with mortared stone. The original mortared stone exterior spandrels were identified next to the interior sides of the 1916 concrete expansion. These original spandrels were 2.5 feet wide and 93 feet long. The exterior edges of each end arch were 77.5 feet apart, exceeding the original bridge plan by 7.5 feet. And here you can see in this bottom image where this 1916 addition was created. The 1792 exterior bridge width was 21.5 feet as planned in 1791, and the original deck was slightly less than 18 foot wide, less than the planned deck. Traces of the mortar stone wing walls were identified at the southwest and northeast sections of the original bridge. So I just want to explain what you're going to see here. This is the 1916 parapet. These are portions of the original 1792 parapet. And this is the original bridge deck as it would have appeared in 1792 up until the 1916 edition. And what we did not expect to find were these internal spandrels, which you'll see more images of in a minute. And again, here's just a side view of the 1916 parapet. You can see the encased concrete here. And this is the original 1792 parapet within the bridge interior. While historic documentation of country bridges, masonry bridges, had set expectations for dirt or gravel infill within the bridge itself, The internal structure proved much more complicated. Excavations between the 1792 exterior spandrels exposed a remarkable and unexpected structural bridge design, possibly the first of its kind and earliest documented in the United States. Rather than homogeneous fill, internal mortared stone spandrels created longitudinal compartments or rooms housing compact stone rubble with little dirt. So here you can see a longitudinal room. Here's a bridge arch top. Here's another bridge arch top. And between the arches are these internal rooms with internal spandrel walls connecting to and mortared into each of the barrel arches. The internal stone spandrels extended between the crown of each arch to the original bridge deck. Two parallel internal spandrels measuring 2.5 feet wide and spaced between 4.5 and 5 feet apart, as well as measuring 60 feet long, span the western to the eastern crowns. West of the western arch, a single internal spandrel existed, measuring 20 feet long. East of the eastern arch, two roughly parallel spandrels were documented, also measuring about 20 feet in length. The internal spandrels were mortared and structurally tied into each of the barrel arches. Data gathered during archaeological monitoring informed digital 3D renders of the bridge design, which better enable documentation as well as illustration of the internal configuration of the original bridge. The identified engineering techniques associated with the 1792 Stone Arch Bridge are the first of their kind archaeologically documented and reported in New Jersey, though the techniques have antecedents in Europe. While not documented in English country bridges, London's 1740 Westminster Bridge, designed by Charles LEDDELL, was constructed with semicircular barrel arches and a gridded pattern of longitudinal as well as transverse internal spandrels, creating square chambers or cellular rooms that were filled with material. In LEDDELL's design, two internal walls parallel to the spandrels were intersected with two perpendicular walls stretching between spandrels, similar to a tic-tac-toe grid. So instead of these long rectangular rooms that we have in our bridge, the Westminster Bridge, as it was originally designed in 1740, in addition to these types of spandrels, had an existing transverse spandrel. And that's because that bridge was much, much bigger and was a two-tiered bridge as well. The 9 compartments in the Westminster Bridge created by the dry laid walls were filled with stone to the road level. In 1740, the use of internal walls and compartments filled with stone with the construction of stone bridges was extremely unusual in London. LEDDELL's design was apparently used to some degree in other British bridges. In the 1770s, the architect of Ireland's Greg Donamana, I think I pronounced that right, bridge over the Barrow River incorporated semicircular arches and internal compartments filled with gravel into their design, likely directly influenced by their experience with or knowledge of LEDDELL's design in England. Princeton Stone Arch Bridge reveals the technique made its way to America as well. Based on LEDDELL's designs, a number of new engineering methods were introduced to the field of bridge building in the 18th century. Among these include ways of pile driving and centering each arch, the use of semicircular rather than elliptical arches, the incorporation of secondary arches over a row of main bottom arches, and the use of reinforced solid interior piers. Brook credits LEDDELL with introducing something absolutely new into British bridge building, that is, the direct use of science to decide questions about construction. LEDDELL also opted not to fill the area between the exterior spandrels with randomly laid rubble, dirt, or gravel. Princeton Stone Arch Bridge incorporates two of these important features, that is, semicircular barrel arches, as well as internal spandrels. While the Stone Arch Bridge lacks the secondary arches present in the Westminster Bridge, here again is just another view of the bridge where you can see these internal spandrels. And here's a profile view looking along the road or along the bridge of Lovelace Westminster Bridge. And here you can see these transverse and longitudinal rooms. So these are the ones oriented parallel to the bridge. And then this is the internal spandrel oriented perpendicular to the bridge. While our bridge has fewer partitions, nevertheless, its architects appear to have been influenced by Lovelace innovations, the science of bridge building, and were clearly demonstrating a level of worldliness and sophistication. This was definitely not your father's country bridge. The Stone Arch Bridge in Princeton was meant to withstand the test of time, and stand it did. A recent study by Antonio Brancich and Camilla Colla of dissected 19th century masonry arch railway bridges in Italy reveals a similar use of internal spandrels, especially in bridges erected askew to water crossings. It's very similar to the way the Princeton Stone Arch Bridge is. Their study indicates that this bridge element, coupled with hollowed piers rather than solid piers, and lighter infill, extended the viability of the bridges despite increased speeds and heavier loads over time. The techniques, once familiar to 18th and 19th century masons, argue Brancich and Colla, were rapidly lost due to the abandonment of masonry arch bridges by the 20th century for new steel structures. The study argues that internal spandrel walls containing light infill within the longitudinal chambers contribute to a bridge's structural performance and stiffening. It helps to avoid relative movement between arches skewed to the river course. It relieves load stresses on pier and arch extrados. Arch extrado is the exterior curve of the barrel arch, and reduces movements between arch rings. Internal spandrels also served a fundamental mechanical function and increased fault load carrying capacities. While in several European examples, the infill is bonded, that is mortared, with the arch extrados, no such bonded infill was present in the Stone Arch Bridge in Princeton. There, all Pallady stone infill was dry laid in each longitudinal chamber, though care was taken by masons to lay the stone infill in a way that minimized voids and maximized points of contact between stones. All of the spandrels, including both the internal spandrels and the exterior facing spandrels of the 1792 bridge, were mortared into the arch extrados and the top of each pier. Admittedly, few masonry bridges have actually been archaeologically recorded during rehabilitation and replacement efforts in New Jersey. The Stone Arch Bridge in Princeton is amongst the earliest constructed in the region and is likely the earliest that has been archaeologically recorded. The documentation provided insight into contemporary bridge construction methods, which may be witnessed elsewhere at other slightly later masonry bridges in the area, such as the Broad Street Bridge over the Assunpink Creek in Trenton, or the Kingston Bridge in Kingston, New Jersey. Identification of formerly hidden internal bridge design provides significant insight into a likely critical design component and engineering technique associated with the Stony Arch Bridge's survival for over 229 years. I just wanted to thank all of the people that were involved in this project, as they were quite numerous. It was a very big project team for a project that was required expedited rehabilitation, as it's a main route through New Jersey. And here you can see the acknowledgements of the main players involved. So thank you very much.